Lab 1, Constant Velocity by Shannon Schechter. The purpose of this lab was to observe the application of Newton's second law of motion in a real-world setting, specifically through the analysis of an object moving at a constant velocity. For this lab, we used two principles. Newton's first law states that if an object is moving at a constant velocity, they will keep moving at a constant velocity unless affected by a net force. We also have Newton's second law, where force equals mass times acceleration. And then we can derive that further to get the final velocity equals the initial velocity plus the net force divided by the mass and multiplied by the change in time. We know that if the last portion of the ride is equal to 0, then the initial velocity is going to equal the final velocity, and that means that there is going to be a constant velocity. We know the mass and the change in time are not equal to 0, so that means the net force is going to equal 0 for it to be a constant velocity. Now we're going to say the objectives and what was the experiment of this lab. We had to record our observation of an object moving at a constant velocity, and then using Tracker we had to get the object's position at corresponding times and construct a computational model via IDLE that accurately demonstrates the observation based on Newton's second law. Then we evaluated the experiment by comparing the experimental data with the computational model, and we made predictions using a spreadsheet. Now, we will look at the video in Tracker over here. And as we can see, the ball is moving towards the negative x-axis, and that is why the slope is in the graph over here is downward and in the negative direction. And now we can see that we started at time 0.133 seconds and position 7.35 e to the minus 2, and then we ended at 1.134 seconds. Now we're going to take a look at the code over here. And we can see that we start with the pulse mass and the position we said before, the velocity that we use this formula over here, that it was the change in position over the change in time, and with the initial time and the change in time over here. Now we're gonna look at this while loop that it's gonna iterate until the final time that it's gonna be 1.168, and we said that the net force will equal to 0 for it to be constant velocity, and over here the pulse velocity is gonna be the formula of the Newton's second law that we mentioned before, and for the pulse position we're gonna update it by using it's gonna equal the pulse position plus the pulse velocity times the change in time, and we're also gonna update the time over here, that it's gonna be the time plus the change in time. Now we're gonna run this code over here. And what we can see is the same movement of the ball, just in the computational model instead of in the video. And if we compare this first graph over here to the last one that we made of the computational model, they're pretty similar. The only difference are these little bumps that have the experiment one, and it's because when we calibrated the ball, it wasn't as accurate as we thought, so there's little bumps over here. But yeah, and like we can see that both graphs are in the negative slope and they are both linear, which demonstrates that in fact the system has zero net force because the slope is the same in each point of the graph, and meaning it has a constant velocity. And now we're gonna see over here using the spreadsheet that there are some discrepancies between the model and the experiment because of the impact the little lifting the black lines of the ball creates on when the ball is moving, and it can also be because with the model we assume we don't have any friction and that it moves under perfect conditions, while in real life this is not as true. And if, when answering the last questions, if we had filmed the object moving in the positive direction instead of in the negative directions, instead of going down into the right, it will have gone up into the right in the positive direction, the slope, and then just from observation it cannot be assumed the types of forces that are acting upon an object. It is not possible to observe and determine the number of forces acting on a system.